we just showed that how to apply the method of conjugate to find the limit of this two-variable function. Another method is to check to see what is the behavior of a two-variable function along different paths. For example, we want to find the limit of this function around the origin. What are we going to do? We're going to check the behavior of this function along x-axis. Along x-axis, it means that your y is equal to 0. So let us simplify the function when y is equal to 0. When y is equal to 0, this function becomes a constant function 1. And when you take the limit of the constant function, it is equal to 1. So again, along x-axis, the limit is equal to 1. Now, what if we want to find the limit of the function along y-axis? Along y-axis, well, x is equal to 0. We're going to fix this value and simplify the function. When x is equal to 0, your function, your original function here becomes 0 minus y squared over 0 plus y squared. But you can cancel out y squared and y squared. You end up with negative 1. You have a constant function. When you have a constant function, the limit is equal to the constant value. So what's happening here? Take a look. The limit of the function, as you're getting closer and closer to the origin, along x-axis is equal to 1. Along y-axis, it's equal to negative 1. You end up with two different values. When you have two different values, it means that the limit doesn't exist. So since the limit around the origin has two different values, we say that the limit does not exist. Now, what if we have a function and we want to check to see what is the limit of the function around the origin? In general, if you want to find the limit of the function around the origin, you can check different paths. Based on the function itself, you can use y equals to mx, y equals to mx squared, y equals to mx cubed, and so on, or square root of x, the third root of x, or in terms of y. Square root of mx, or y can be mx to the fourth, or the third root of mx, and so on. So your goal is to simplify the function as much as you can so you can take the limit. Well, each function has a different behavior. Let's take a look at a couple of examples. Investigate the limit of x plus y to the second divided by x squared plus y squared around the origin. Okay, around the origin, we have different paths. Remember that the domain of this rational function is everything in the plane except for the origin. The origin doesn't belong to the domain of the function, but we can find the limit around the origin. That's absolutely fine. What are we going to do? We're going to use y equals to mx. Again, This is just pure practice, everyone. And we're going to select this to help us simplify this function. Very good. The limit of x plus y to the second divided by x squared plus y squared along y equals to mx, it helps us to simplify the function. This function now can be written in terms of one variable. So from two variable function to one variable function. Okay, let's simplify this as much as we can. We can factor out x squared. So when you factor out x squared, you end up with 1 plus m to the second. On the denominator, also factor out x squared. You get 1 plus m squared, and x goes to 0. But here you can cancel out x squared and x squared. These are common factors, everybody. So here you have 1 plus m squared divided by 1 plus m squared. But please note that when you're writing it this way, it means that the limit depends on the value of m. If m is equal to 1, then the limit is equal to 2. When m is equal to -1, limit becomes 0. When m is equal to 0, the limit is equal to 1. Well, what's the meaning of that? It means that I don't get a unique limit value. So the limit doesn't exist. Because the function approaches different values along different paths, we conclude that the limit doesn't exist. So in general, when you have your function simplified into a quantity that has m in it, it means that the limit depends on the value of m, and it definitely doesn't exist. The limit depends on m, and we have different choices for m. So as you can see, it gives you different limit value. So you're going to say that, hey, the limit doesn't exist. So I just showed you how to use two paths, finding the limit, and also I showed you how to use a general path to check to see if the limit exists or not. Now we're going to investigate a more general approach. Here you have the limit of x squared divided by x squared plus y squared as x and y getting closer and closer to the origin. If the limit exists, then we expect the values of our function in the given table to be closer and closer to a z value, which is your L. If you plug in different values, like x is 0.1 and y is 0. X is 0.1, y is 0.1. X is 0 and y is 0.1. So we are getting closer and closer to the origin. Here we are using smaller values that are closer to the 0 as well. We get different values for our z. We can take a look at our table here and check to see if I plug in different values for x and y, what happens to the z value of this function. Well, take a look. My x is negative 0.5, then negative 0.4, negative 0.3, negative 0.2, negative 0.1. My x can be 0 itself, 0.1, 0.2, 0.3, and so on. And on the vertical column here, I have values for y, 0.5, 0.4, 0.3, 0.2, 0.1, 0 itself, and so on. Negative 0.1, negative 0.2, negative 0.3, and so on. So if I plug in, for example, negative 0.3 and 0.4 into my function, the z value becomes 0.36. If I plug in, for example, negative 0.1 and let's see, 0.1 itself into my function, the z value that I'm getting is 0.5. If I plug in 0 into my function for my x and my y is equal to, for example, 0.1, the value is 0. But if I plug in 0 and 0 into my function, well, it is undefined. So what's the meaning of that? The behavior of this function in the plane in 2D, in 2D, the reflection in XY plane is like this, right? They're getting closer and closer to 0 from different paths is shown in 2D down here. The limit along x-axis, your y is equal to 0. So you end up with x squared divided by x squared plus 0. You can cancel out x squared and x squared. You end up with a constant function 1, so the limit becomes 1. Now along y-axis, x is 0. X is fixed and it is 0. The limit of the function, if you simplify this, you get 0 divided by 0 plus y squared. You get constant function, which is 0. The limit is 0. These two values are not equal to each other. What's the meaning of that? It means that the limit of the function doesn't exist around the origin. So this is the numerical approach, and also showing you when you plug in two fixed values like x equal to 0, y equal to 0, and simplify your function, you get two constant functions. And since you have constant functions, the limits are equal to those constant values. And in this case, as you can see, they are not equal to each other. So the limit doesn't exist.